Hello guys, welcome back to this topic of elastic waves. So in this session, we are going to study the elastic waves in a cubic crystal. So elastic waves are the waves when a medium vibrate elastically. When a medium vibrate elastically, the elastic waves are generated. So the important property of these elastic waves is that when they are propagating through a medium, no energy dissipation takes place. Energy dissipation is not there. Such kind of waves are called as the elastic waves. So here I have considered a cubic crystal, or I have considered a cube as shown in this figure, which is having the volume delta x, delta y, delta z as shown in the figure. So because the edges of this cube are like this, this is delta x from this to this is delta y, and this is delta z. So the volume of this cube is delta x, delta y, delta z. And suppose a stress hx of x acts on the face ABCD. This is the face ABCD. This face is there. And here a stress means it is the force per unit area is called as the stress. So that is acting on the face ABCD. And this ABCD is at a distance x, small x, from the origin. Origin is here. I have taken a three-dimensional coordinate axis. And also, you imagine that another force given by this another stress means force per unit area. Again, another stress given by hx of x plus delta x, which can be written as hx of x plus dou hx by dou x into delta x. It acts on the opposite face of this ABCD, which is EFGH. This face is there. So this force is acting in this direction. This stress is acting in this direction. So because of stresses, the strain will be developed in the medium. Strain means the changes in the dimensions of a body is called as the strain. And so hence the resultant force. What is the resultant force acting on this cube? The difference of these two forces, because these two forces are opposite to each other. They are in the same, they are in one direction, but they are opposite to each other. So that is why we have to subtract these two forces to get the resultant force. So this is the force acting on the face EFGH, and this is the force, stress acting on the face ABCD. And when you subtract these two, we are getting dou hx by dou x into delta x as the resultant force acting on this cube in the x direction. That is very important. Okay. So since the area of each face is delta y, delta z, the resultant force on the cube is dou f hx by dou x into delta y, delta z is the area into delta x. This delta x comes because of the difference in the force. So this is the resultant force acting on the cube in the x direction. Okay, so in the x direction. So next, this is the resultant stress or force, both are same. And delta y delta z is the area, because you can see in the diagram So delta y is this one, delta z is this one. So this area, on this area, some force is falling. So that force divided by this area gives this stress. Hx of x is the stress. So stresses x, y, and x, z also act on the cube, and these have also their components in the direction of x-axis. So what happens here? We have shown only the two stresses which are along the x direction, one on this face and another on this face. We have shown the only two stresses we have shown here. So the stresses are also present on other faces of this cube, and hence a component of their stresses acts along the x-axis. That is the important point. So that is why stresses x, y means the stress on the other face, which is in the y direction. So is another stress in the z direction is there. Their component are xy and xz. Xy and xz are the components of the stresses which are acting along y-axis and z-axis. Stresses are acting y and z-axis. Their components, these xy and xz, acts along the x direction. So that is the point. And thus the net component of force on the cube in the x direction is given by. So the net component of force, stresses or forces in the x direction is given by this equation. So we have added all the components along the x-axis. That is why it is written as a Fx. Fx means the net force along the x-axis, and these are the components added together. So this is first component, second component, third component, delta x, delta y, delta z. Suppose u is the displacement in the x direction due to the above component of the force. So here some resultant force is resulted because of these two stresses which are acting in opposite direction. So since these are not equal and opposite, they are opposite but not equal. That is why some resultant is produced here. So this resultant stress can produce some displacement of the cube. So let that displacement be u. So u is the displacement in the x direction due to the above component of the force. If rho naught be the density of the material of the cube, then its mass will be equal to rho naught into delta x, delta y, delta z. So actually density is equal to mass divided by volume. So therefore mass is equal to density into volume. So this is density, and delta x, delta y, delta z is the volume. So this product gives the mass of the material of the cube. And the equation of motion in this case will be can be written in this way. So rho naught delta x, delta y, delta z into dou square u by dou t square is equal to this. Actually, this is the LHS of this equation, force equation, RHS of force equation. So this RHS of force equation is written as it is, but this force f of x is written in some other form. That is according to Newton's second law. According to Newton's second law, F is equal to ma form we have written. this Fx force. So it's all m mass. Rho naught into delta x, delta y, delta z is the mass of the material of the cube. And this dou square u by dou t square is the acceleration, because u is the displacement. So therefore, dou square u by dou t square gives the acceleration of the displacement of the acceleration of the wave propagating in x direction. So this is equal to the RHS of the above equation. So here this delta x, the volume get cancelled on both sides. So here also volume is there, delta x, delta y, delta z. Here also delta x, delta y, delta z is there. You can cancel out these two. So you are left with rho naught dou square u by dou t square is equal to this much. This is the force component of stresses in x, y, and z directions. This is the equation 1. So this is all we worked out for the stresses acting along the x-axis. So we can write similar equation of motion for the y and the z direction. So this is the equation of motion in the x direction. That's why you can see here x comes, that indicates that you are in the x direction. So for an isotropic body of cubic crystals taking the xy and z directions to be parallel to the edges of the cube. So that so we have taken these x, y, and z directions parallel to the edges of the cube as shown earlier. So these are the edges of the cube and these are parallel. X-axis, y-axis, z-axis, they are parallel to the edges of the cube. In that way we have taken. So we write the stress, we write these things, the stress along x direction is given by this C11 Exx plus C12 Eyy plus Ezz. I will tell what are these. And this is stress along the y direction, and this is the stress along the z direction. So in this equation, the C11, C12, C44 are the elastic stiffness constant or moduli of elasticity. They are referred as the elastic stiffness constants or moduli of elasticity. And these things, what are Exx, Eyy, Ezz, Exy, Exz are the strain components in different directions. These things, Exx, Exy. So Exx means it is a strain component along the x-axis. This is the strain component along the y-axis. This is the strain component along the z-axis. So this is a strain component due to stress in the y direction, but in the along the x-axis. Similarly, this is the strain component due to stress on the z-axis, but and this is the component along the x-axis. So all these are the strain components, and these are all stress components. So as you know, the Hooke's law is applicable here. Hooke's law tells that stress is directly proportional to strain, or stress is equal to some constant into strain. So that is why these are C11, C12, C44. These are some constants, elastic constants. They are referred as the elastic stiffness constants or modulus of elasticities. And next what we are doing, substituting 2 into 1. This is the equation 2, and substitute this into equation 1. Equation 1 is here. That means the wave equation. In the wave equation, we have to substitute all this. This x, 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 y, x, z are there. We have to substitute those values. So it comes like this: rho naught du square u by dot square plus what is that? Dou xx of dou x is there. So that xx means it is C11. It's all we have to substitute. Then we have to simplify. Then only we will get this equation 3. And so here up to here it is hx substituted. And next C44 is common here. That's why we are writing C44 is common. And these are the dou exy, dou y plus dou exz, dou z. So this part is there. Means for xy and xz, we have combined together. So this is that part. So that's all for the first part. So we obtained, sorry, I was here. So we got equation 3 in this way. We substituted the equation 2 into 1. Slight simplification is needed. So we got this equation. So next, these C, as I explained, these are the elastic constants C11, C12, C44, and which have the dimensions of force per unit area because they are the proportionality constants here. Stress comes. Stress is because this is C1, for example, C11 is equal to stress by strain. Strain is a non-dimensional quantity, but stress is a dimensional quantity whose dimensions are force per area. So that is why these C11, C12, they have the dimensions force by area. And these are all the strain components. Next, the elongation or extensional strains are given by. That means the strains are produced in different directions. We are writing in this way. E double x is equal to dou u by dou x. So use the use the displacement. It is along x-axis. So it is some type of strain. Elongational strain. Elongational strain means some change in length to the original length. So that's called as the strain. Longitude, what is that? Elongational strain. So it is in the x direction, y direction, z direction. And shearing stresses are given by, shearing strains are given by EXY because shearing stress will be there, HXXY. That's why strain is also the corresponding EXY strain. So this is EYZ, this is EZX. So these are the strains in some other directions. It means XY plane. It is in XY plane, it is in YZ plane, it is in ZX plane, like that. Now we have to substitute equation 4 and 5 into equation 3. This is equation 4, this is equation 5, and this is equation 3. So here, all these things are there. In equation 3, EXX is there, EYY is there, EZZ is there, EXY is there, EXZ is there. All these things we have to substitute and then simplify. After simplification, we get this equation. Equation 3 comes or turns into this form. So if you want to see how this became, you can go through here. Just I will show you. So this was the equation 3 and equation 4 is like this, equation 5 is like this. So you are substituting 4 and 5 into 3. That means just I will show you. So this part, no substitution in LHS side. in RHS side, C11 rho by dou x Exx is there. C11 rho by dou x Exx means dou u by dou x, dou u by dou x, that you are substituting. Plus C12 dou by dou x of Eyy. Eyy means dou v by dou y, that we have to substitute. Plus dou by dou x of Ezz. Ezz means dou w by dou z. So in this way you substitute. Plus C44 and dou by dou y of Exy. Exy means this one. Dou v by dou x plus dou u by dou y means Exy, that we have to substitute here. So dou by dou y of this quantity plus dou by dou z of Exz. So dou by dou z of Exz. Exz is here. So this we have to substitute. Then we have to simplify. So yeah, let's just write as it is. So this part you write as it is, and here C12, and this we have to differentiate. This is dou square v by dou x dou y, this one, plus this one means dou square w by dou x dou z, so that you have written, plus C44, and this is, you see, dou square v by dou y dou x, dou square v by dou x dou y or dou y dou x, both are same, plus this one dou by dou y of dou u by dou y, that is dou square u by dou y square, so it's also written, plus C44 we have to write again, and this term, so it is dou by dou z of dou u by dou z, so that gives dou square u by dou z square, plus dou by dou z of dou w by dou x, so this gives dou square w divided by dou x dou z. So in this way you differentiate it. So then you make some rearrangement of the terms. In this term you write as it is, and C44 term comes 2 times, so two things are there. So this kind of thing, make first one group, dou square u by dou y square plus dou square u by dou z square. In these two cases, C44 is common, so C44 into this quantity, plus this C12 and C44 is also at 2 places. C12 is multiplied by this term, but C44 is also multiplied by this term, dou square v by dou xy plus dou square w by dou x dou y. So this C12 is also multiplied by these two things. So you take C12 plus C44 as a one group, and you write the remaining group as dou square v by dou xy plus dou square w by dou x. So in this way, you got the resultant equation, that is here. Equation 6, we got the equation 6. As wave equation for the this equation 6 is the equation of the wave for the wave moving in the x direction. Similarly, we can write for the y and the z directions. So next we are here. So these are the two equations written for y and z direction. So this is for here v comes. V is the displacement in the y direction. So this is for y direction, and w comes. So w is the displacement along the z direction. So these are the two equations just we wrote in analogous manner. So these equations have to be solved for spatial direction of the propagation of the waves in the crystals. Now we'll see the wave velocities in the 1000 direction. What is this 100 direction? Just I will show you. Here is there. You see. So these are the crystal directions. I already explained in one of my session. So this x-axis, along the x-axis is the 100 or 100 direction. Y means 010 direction, and Z means 010 direction. So these are called as the crystal directions. So in the crystal directions, we assume that this wave is propagating in the 100 direction. So here two cases arises. Case 1, let the solution of the equation 6 is given by a longitudinal wave of this form. U is equal to U naught e raised to I omega t minus kx. So first we assume that wave is longitudinal in this case. So U is the component of particle displacement in the x direction. This k is a wave vector having its normal meaning. And omega is the angular velocity, is equal to 2 pi nu is the angular frequency. The wave vector as well as the particles in this case move along the edge of the cube in the x direction. So now what I will do, this is the equation number, just I will check, 7, 8, this is equation 9. So I am differentiating equation 9 twice with respect to t, means time. So this is one time differentiation. This is another time differentiation. So when you differentiate one time, here I omega comes. When you differentiate again, this I omega again repeats, so that gives square. So this I omega square, this I square is there. I square is a complex number, its value is -1. So, and this u naught into e raised to I omega t minus kx, I have written again that as a u, because u is given by this, u is equal to u naught e raised to I omega t minus kx. So this part you can write as this is all u and this is omega. So it is minus omega u square. Then differentiating this equation and again with respect to x now twice. This is the one time differentiation. Here minus ik comes because now you are differentiating with respect to x. So x is here. Again differentiate one more time. One more time it appears. So when it appears second time, this negative sign vanishes. But this I square is there. Again it gives minus sign. And this is again u naught into e raised to I omega t minus k is kx is the u. And that means u into k square. U into k square minus n comes because of this I square. So in this way, I got equation number 10 and 11 and substitute equations 10 and 11 into 6. 6 means our this equation, earlier equation. So this is the equation 6. In this equation, we have to substitute those two. What are those? Equations 10, equation 10 and 11 are like this. So rho naught into dou square u by dou t square is there. So now its value according to equation 10 is minus omega square u. You have written minus omega square u is equal to C11 into C11 into dou square u by dou x square. I will go to equation number 6. Dou square u by dou x square. What happens to these two terms? These two terms vanishes here because they are the terms along the y and z axis. So these two terms vanishes. So only first term is retained. So that is why here C11 into dou square u by dou x square. So from equation 11, dou square u by dou x square means minus k square u that we have written. And a rho naught dou square u by dou t square was there. So from equation 10, it is minus omega square u. So substitute these two values. And what happens? This u get cancelled, negative sun get cancelled. So this becomes omega square by k square is equal to C11 by rho naught. Or you write omega by k is equal to root of C11 by rho naught. Then by definition of that means according to the relation connecting the velocity, frequency, and wavelength of a wave. So UL means the velocity of a longitudinal wave is equal to F lambda. Here F means nu is there. So nu is the frequency, nu lambda we have written. So this is equal to omega over k, and this omega over k is equal to this one, root of C11 by 1. And because this omega over k is the phase velocity, is called as the phase velocity of a wave train. So that is why omega by k is taken as the velocity. Phase velocity. Phase velocity means it is velocity of one wave is called as the phase velocity. Single wave. So this gives the velocity of longitudinal wave in the 100 direction. Next, we consider, now we assume that the wave is of transverse in nature. So transverse, here wave moving along the edge of the cube in the y direction with the particle moving in the x direction. So here the vibrations are along y direction, but the particle is moving along the x direction. So that kind of situation it is. And but now we have to think that the wave is transverse in nature. That means the vibrations are perpendicular to the direction of propagation of the wave. That is called as a transverse wave. So again, we assume that the solution is of this form. U is equal to u naught into e raised to I omega t minus ky. And as usual, we have to differentiate this with respect to time twice and with respect to y twice. So with respect to time twice gives this one. So after substituting all these things, just like how I did for the longitudinal wave. So cancel this omega, and we write omega square by k square is equal to C double 4 divided by rho naught, or omega by k is equal to root of C double 4 by rho naught. So what happened? This is again, we are getting an expression for velocity. Now this is the velocity of a transverse wave is equal to nu lambda or f lambda. So it is again is equal to omega over k, since omega over k represents the velocity of a wave, phase velocity. So this is equal to root of C double 4 by rho naught. So in this way, I got an expression for velocity of a transverse wave in the x direction and velocity of a longitudinal wave in the x direction. So this gives the velocity of transverse waves in 100 direction. If the longitudinal and transverse waves velocities are experimentally determined in the above direction in a crystal, we can determine the elastic constants C11 and C44. So this constant C here C44 is there, and earlier it was C11. And these two constants can be determined if the velocities are determined experimentally. So it's all about the velocities of the elastic waves in 100 direction in an elastic material, in an elastic material. So this was the elastic material we had considered. So when the stress is given to this elastic material, it starts to vibrate, liberating the elastic waves, and we argue that these elastic waves are propagating in the x direction window, and we all solved. So it's all about the elastic waves. Thank you for listening.